7.3, solving trigonometric equations. This is the only section that we're going to do this week because it is really important. I am going to be using my calculator, and I do like to solve all these equations in degrees because I think it makes sense, more sense. I know the online homework likes the answers written in radians. So at the end of all these solutions, I will change everything to radians, just to show you how to solve things in radians. So I want you to make sure on your calculator that you are in degree mode, right? So my calculator right now is in radian mode. So I'm going to make sure I change that to degree because when I solve these, I want to make sure my calculator is going to give me answers in degrees. All right, so when we solve trigonometric equations, the first thing we need to talk about are the fundamental solutions. Okay. Now, when we say fundamental solutions, we mean all the solutions in one period of the equation. All the solutions in one period. So remember the period of sine and cosine is 0 to 2 pi. The period for tangent is 0 to pi only. And if we have an omega value, okay, which changes the length of the fundamental period, we're going to find all the fundamental solutions in the period of the equation, right? Next, we're going to talk about a general formula for the solutions. So the general formula, because our sine, cosine, and trigonometric equations are periodic in nature and they go on forever, right? They're sinusoidal. They have infinite number of solutions. So what we're going to do is we're going to add the fundamental period k to each one of our solutions. So for example, okay, if we had a solution 45 degrees and 135 degrees, okay, these are our fundamental solutions. If I wanted to write those as a general formula, okay, and say the period for our function was 2 pi or 360 degrees. What I'm going to do is I'm going to write the general formula as 45 plus 360k. Let me just put theta equals here. And theta equals 135 plus 360k. Now what is this k value? K is an integer. Is an integer. And this is going to represent all the solutions. So if k was 0, we'd have 45 plus 360 times 0. And that would give us our fundamental solution. Okay, so if k was 0, if k equaled 0, we get 45 plus 360 times 0. And we get 135 plus 360 times 0, right? And so this would give us our fundamental solutions. Now, if k was positive 1, if we let k equal 1, then we get 45 plus 360 times 1. And we get 135 plus 360 times 1. And so 45 plus 360 is 405 degrees, and 135 plus 360 is 495 degrees. Now what this k value represents really is how many times around the unit circle we're going to get those values, right? So 45 degrees and 405 degrees are coterminal, right? They're both in quadrant 1. They both have reference angles that are equal. Same thing with 135 and 495. They're in the same location on the unit circle. So we could let k equal 2, and we could add basically 720 to both of these solutions, and that would give us yet 2 more solutions. Now, since k can be an integer, and integers are both positive and negative, I just want to show you if k equals -1. That means we're going to have solutions 45 plus 360 times a -1. So basically that's 45 minus 360. And 45 minus 360 is equal to negative 315 degrees, right? And let me go ahead and do the other one. 135 plus 360 times -1. So 135 minus 360 is minus 225 degrees. So negative 315, I just want you to realize this, is if we were to start on the x-axis and rotate clockwise 315 degrees, 315 degrees lands in the same location as 45, and it lands in the same location as 405. All of these solutions, okay, the fundamental solution plus 360 times 0, the fundamental solution times 360 times 1, and the fundamental solution plus 360 times -1, they all correlate to the same location on the unit circle. One, we're just rotating that short distance. The second one, we're going all the way around, plus 45 more degrees. And this one, we're going clockwise, 315 degrees. And all of those are in the same location. This one, 135 degrees, if you guys remember, is over here, right? But that's the same thing as going 495 degrees. 495 degrees is all the way around, plus another 135, okay, so it's in the same location. Negative 225 is when we rotate clockwise. But all of these solutions are corresponding to the same point on the unit circle. So when we write a general formula, we're going to take our fundamental solutions and add the period times k to all of our fundamental solutions. The third thing we can do is we can list 6 solutions. All right, and so here we already have 6 solutions, right? But sometimes they will ask you to list a bunch of different solutions. So you could let k equal 0, 1, and 2. You could do 1, 2, and 3. But you just need to come up with 6 different angle measures that is in the same location as one another, right? But different angle values. So I'm going to list 45 and 135. I'm going to list 405 and 495. And then I'm going to list negative 315 and negative 225. Okay, all of these angle measures are solutions, okay, for this particular example. All right, so I have 9 examples that I would like to work through. I'll do the first few on the first video, and then I'll do the latter ones on a second video. But I'm hoping to get through all of these 9 examples in 2 videos. All right. So example number 1, right? Let's go ahead and solve this equation. Sine theta equals 1/2, right? So we want to find all the angles that sine of that angle is 1/2, okay? Now what I can do here is I can use the inverse trig functions. Okay, if I wanted to cancel sine, I'm going to do sine inverse of both sides. Now I want you to remember the calculator is only going to give you a solution in quadrant 1, right? Because sine inverse is positive, and so it's going to give us our quadrant 1 location, right? So I'm going to go ahead and type that in, right? Sine inverse of 1/2. Now, if you remember what this angle is, you're ahead of the curve here, but when I hit enter, it's going to give me 30. Now, we're in degrees, so that's 30 degrees, right? So I know that one of my angles is at 30 degrees. Now the sine value is 1/2, and the sine value is the y value. So this is at some x, comma 1/2, right? Now you might recognize this point on the unit circle as rad 3 over 2, 1/2, but I'm just going to leave it at x for now, okay? So this is our one solution that we get from the calculator, okay? Theta equals 30 degrees. But the fundamental solutions are all the solutions from 0 to 360, right? Because the period of sine is 2 pi, or 360. So I want all the solutions from 0 to 360, right? So let's go ahead and first find all fundamental solutions. All right, so since the period of this function, okay, is 2 pi over omega, notice our omega is just 1 here, so we're just going to get 2 pi over 1, okay, or 2 pi. Now I am going to convert this to 360 degrees, right? So from zero, rotating all the way to 360 degrees, I need to look for another value that has a y value of 1/2. Okay, so y of 1/2 is here. So y is also 1/2 on this other side, right? And this point is negative x, comma 1/2, right? And so what angle is that? Well, the reference angles are going to be equal. But when rotated from 0, we get 30 degrees and 150 degrees, basically. So our fundamental solutions are 30 degrees and 150 degrees. That's the only two angles from 0 to 360 that we're going to get a sine of positive 1/2. Down here in quadrant 3 and 4, we're going to get a sine that is negative, right? And we're not going to count those, right? So here is all our fundamental solutions. So the second thing we want to write is write them as a general formula. And so since our period is 2 pi, or 360 degrees, the general formula is going to be 30 plus 360k and 150 plus 360k, right? So this is going to represent all the angles that have this particular, that solve this equation. Okay. So the third thing we can do is list 6 different solutions. Right? And so by doing that, I'm just going to start adding 360k. All right. So I have an answer at 30. And then if I let k equal 1, I'm going to take 30 and add 360 to it. All right. And get 390. And I can add 360 to it again and get another angle, 750. Okay. Now the other thing I could do is I could start with 30 and start subtracting 360, meaning we're going counterclockwise, or we're going clockwise. So we could get negative 330. I could subtract 360 from it again to get another angle, negative 690, and then I need one more. So let me go ahead and subtract 360 again and get negative 1050. All of these are solutions, right? Now I just used the first fundamental solution to find all 6. That's perfectly fine. But I could also use the second fundamental solution to find 6 more. Let me go ahead and do that. So if k was 0, I get a solution of 150. And then to 150, I'm just going to start adding 360k. So I'm going to let k equal 1 and add 360 once to get 510. Okay, I'm going to add 360 again, and that's adding 2 360. So that's if k is 2, and I'm going to get 870. All right. Or if I wanted to find some negative angles, I would let k equal negative 1, which means I'm going to subtract 360 to get negative 210. Subtract 360 again, and that would get me negative 570. Subtract 360 again, and get negative 930. Okay, this is a 7. Sorry about that. Right? So for each different equation, we want to find the fundamental solutions and write as a general formula, at the very least. Okay, if we need to list 6 different solutions, we can do that if we wanted to. All right, so let's solve a tangent. Okay, example 2. Say we have tan of theta equals 1. Okay, so if I were to solve this using inverse tangent, okay, to get theta by itself, I'm going to tan inverse both sides, right? So I'm looking at the tan inverse of 1. Now the calculator is only going to give me one solution, but that one solution is a good starting point, okay? So if I do tan inverse of 1, maybe you know this answer, right? What angle would give you a tangent of 1? Okay, the answer is 45 degrees, right? All right, so we want to find all the fundamental solutions, okay? So number 1, let me go ahead and here, find the fundamental solutions. Those are all the solutions within one period. Okay, so if I were to look at this equation, tan theta equals 1, what would be the period of this function? Remember, tangent has a period pi over omega. And since pi over omega, and since omega is 1, we just get a fundamental period of pi. Okay, so all of our fundamental solutions are going to be between 0 and 180. Right? So if I look at the unit circle here, I have my first angle at 45 degrees. Okay, that's going to give me a tangent equal to 1, right? So from 0 to 180, okay, in one fundamental period, that's answers in quadrant 1 and quadrant 2. Now, if you remember, in quadrant 2, from all students take calculus, right, only sign is positive here. So tangent happens to be negative here. So this equation only has one solution, and it's only one fundamental solution, right? So that is the only answer we have to find, okay? So the second thing we're going to do is we're going to find our general formula. And so to get the general formula, we want to add pi k to our fundamental solution. So we're going to get theta equals 45 plus 180k this time, because the fundamental period of tangent is only 180 degrees, right? Now, if we want to, let me add something else here. Say we want all the solutions, find all the solutions from 0 to 360. Okay, scoot that over for you. All right, so if we find all the solutions from 0 to 360, that's just a matter of rotating, okay? We can use our k values here. So 45 is one of the solutions, and then if I add 180k to that, 45 plus 180, is that less than 360? Right? Yes, it is, right? So if I add 180k, I'm going to get 225 degrees. Now, if I add 180 again, then I get 405 degrees. So that's a solution, but it's not within this restricted domain of theta, right? So, and if I were to subtract 180, I get back to 225. If I subtract 180 again, I get back to 45. If I subtract 180 again, now I'm to negative 135. But that's not from 0 to 360 either. So we have two solutions from 0 to 360. So on the unit circle, where is 225 degrees? Right? It's in quadrant 3. It's that other angle where tangent is positive, right? All students take calculus. Tangent's going to be positive in 1 and 3. And so that's where we have this reference angle of 45 degrees, right? Now, in terms of fundamental solutions in the general formula, this will get us all of them, right? It'll get us the 45 and then the 225, and then keep going around and around, okay? We'll just kind of toggle between these two locations on the unit circle, all right? Now, in radians, let me just convert it. 45 degrees is pi over 4, and 180 is equal to pi radians. So in radians, we would look at pi over 4 plus pi k, and here we're looking at pi over 4 and 5 pi over 4, right? So you just need to convert these to radians for the online homework. All right, let's do another one. Example 3. Let's do 2 sine theta plus rad 3 equals 0. So in order to solve this one, I want you to get the trig function by itself, okay? So solve for sine theta first, and then we can use our inverse sine at that point. So the first thing I'm going to do is I'm going to move the rad 3. So I get 2 sine theta equals negative rad 3. And then solving for sine, I'm going to divide both sides by 2. So I get sine theta equals negative rad 3 over 2. Right? Now, to solve for theta, to find angle theta, that's the solution to this equation, I can sine inverse this. Okay, so when I sine inverse negative rad 3 over 2, the calculator is going to give me an answer in quadrant 4. Remember, sine inverse was restricted to quadrant 1 and quadrant 4, and it's actually going to write it as a negative angle. So when we do our fundamental solutions, we're going to have to be really careful here, right? But let me go ahead and solve for theta here. Okay, so sine inverse negative rad 3 over 2. Right, make sure your division is not underneath your square root symbol there. All right, so we're going to get negative 60. So that shouldn't shock you, all right, that negative 60 angle. So let me go on a unit circle here. And negative 60 is down here. Okay. All right. So when we find all the fundamental solutions, they're within one period of our function. Okay, so this period of this function again is 2 pi over omega. Okay, omega is times our angle here, so we get 2 pi over 1, which is just 2 pi. Okay, so our fundamental period is 360 degrees. Now really what we need to do, all of our fundamental solutions, we need to find theta from 0 to 360 degrees. And our calculator just gave us an answer, negative 60. Negative 60 is not a fundamental solution, right? We have to write this as a positive angle, okay? So negative 60 as a positive angle would be 300 degrees, right? So my first fundamental solution is going to be, I don't know where to write it, is actually going to be 300 degrees, right? Negative 60 doesn't count. Now, on these fundamental solutions, we're solving a sine, right? And remember, sine is the y-coordinate. So this is x, comma, negative rad 3 over 2, right? Now, I know we know what the x value is, right? But I want the y value, the sine value, to be negative 3/2. Theta, guys, this is theta here, right? So sine of theta is going to be negative rad 3 over 2. So where else on the unit circle do we get a sine of negative rad 3 over 2? Well, that's going to occur across the way, right? And this is where we're going to get negative x, negative rad 3 over 2, right? These 2 points will have the same sine value. So where is that? Well, it's, a reference angle of 60 degrees, but in quadrant 3. So how many degrees is that? When rotating from 0, we're going to go 180 plus 60 more, which gives us 240 degrees, right? So our fundamental solutions, not only do they need to be within, not only do they occur every 360 degrees, but our fundamental solutions should start at 0 to 360. Okay, so the calculator actually doesn't even give us our first fundamental solution. We had to convert it, right? So here's our 2 fundamental solutions, and then so the second thing I want to do always is find the general formula, which is adding the period to each one of our fundamental solutions, right? So we're going to get theta equals 240 plus 360k, and theta equals 300 plus 360k, right? Now, in radians, we're looking at 1 pi, 2 pi, 4 pi, and 5 pi. So we're looking at 4 pi over 3 plus 2 pi k. That would be the answer in radians, and we're looking at 5 pi over 3 plus 2 pi k, right? But just convert your degrees to the radian measure for the online homework. Right? Either way, on the quiz and on the test, I accept answers in degrees. All right? I'm just showing you this so that you can get the right answer on the online homework. All right, so let's do 4 and 5 here. So let's do sine of 2 theta equals 1/2. All right, so if I wanted to solve this for sine, I could sine inverse both sides, and that'll cancel this sine, and that'll get this by itself, right? So I'm going to go ahead and sine inverse both sides, This is number 3, right? Or 4. 1, 2, 3. This is number 4. Okay. So sine inverse here. It's going to get those to cancel. So I get 2 theta. And then sine inverse here. Sine inverse of 1/2 is 30 degrees, right? 30 degrees. Now that's what 2 theta equals, right? And so to find the fundamental solutions here, okay. What is the period of this function, right? The period of this function is 2 pi over omega, right? And omega this time is 2. So the fundamental period here is just pi, or 180K, right? Now, I didn't do this. I probably should have. We really should have done a substitution, okay? Let x equal 2 theta, right? And solve this for x. So instead of 2 theta equaling 30, I'm going to let x equal 30, right? And I'm going to find all the fundamental solutions for x. So 30 degrees is here, okay? And we have an x value and a 1/2 value. So where else is the sine equal to 1/2, right? The y value is the same over here on the other side of the y-axis with a reference angle of 30. This is going to be the point (-x, 1/2), just like it was before, right? So x has 2 fundamental solutions, 30 and 150, all right? But we're not trying to solve for x, we're trying to solve for 2 theta. So what we want to do here is find all the fundamental solutions for x and then convert it to theta. All right? Let me scoot that over. Find all the fundamental solutions for x first. So the fundamental solutions for x are x equals 30 plus 360K, and x equals 150 plus 360K, right? But remember, we're not trying to solve for x, we're trying to solve for 2 theta. So I'm gonna make this substitution back, right? I get 2 theta equals 30 plus 360K. I'm going to leave a space here. And I get 2 theta equals 150 plus 360K. Right? So if your period, or if your function is a double angle or has some other period other than 360, find the fundamental solutions for x first with the normal period and then switch it. Right? So if I wanted to solve this for theta, I need to divide both sides by 2. I'm going to go ahead and solve both of them. So this is going to get me theta. Now here, I need to divide 30 by 2 and 360 by 2, right? Because I need to make sure I'm dividing everything. So 30 divided by 2 is 15, and 360 divided by 2 is 180K, right? And so then my other solution is going to be 150 divided by 2, which is 75, plus 360 divided by 2, which is 180K, right? So here is our fundamental solutions, 15 plus 180K and 75 plus 180K. Now, the reason why this happened, let me go ahead and show you on a graph. Right? Normally, sine is 2 pi periodic, right? So we're going to get a sine curve. Oops. Here, here. That goes up, comes down, like this, right? This is our normal sine x. So when we have sine of 2 theta, what happens is that the period is now pi. So a whole cycle of sine needs to fit here. Okay, so it's kind of halved. It's going to go up, come down, it's going to go up, come down like this, right? So this is sine 2 theta. And so we're looking for where these functions are a half, right? So a normal sine function only has 2 solutions, right? It's going to have, corresponds to the 30, and this corresponds to the 180. A sine 2 theta is also going to have 2 solutions on its fundamental period, but they're scooched over, right? They occur before these other 2. They're going to occur at 15 and 75 degrees, right? Here and here. This is where the sine value is 1/2. And not only that, but it's going to have more than 2 solutions from 0 to 360, right? So we found all the fundamental solutions for x, and then what did we do? We substituted x for 2 theta, and then we found the fundamental solutions for theta. Right, by using some algebra. Now what I'd like to do is I'd like to do a third one. I'd like to find all the solutions from 0 to 360. Okay. And so what we're going to do is we're going to take these fundamental solutions and just start listing them out. If it falls between 0 and 360, I'm going to write it down. Right? So the first one we have is 15 degrees. And then if I subtract 180, right, we're going to get a negative angle. I don't want that. So 15 plus 180, 15 plus 180 will get us a second solution, which is 195, right? And if I add 180 again, then I get a solution at 375. Well, that's outside of that range. I don't want that one. So I'm going to go to my next fundamental solution. If I let k equal 0, I get a solution at 75. Again, if I subtract 180, that's going to get me a negative angle. I'm not interested in that. But 75 plus 180k is 255, right? And 255 is within this domain. Okay, if I add 180k again, I get 435, which is a solution. It just doesn't fall between 0 and 360. So these are all 4 angles that give us a sine of 1/2. And those 4 angles correspond with where the purple graph here is equal to 1/2, right? So our normal function only had 2 solutions, 30 and 150. Our sine 2 theta had 4 solutions, right? All 4 here. All right, I know that was a little tricky, but we're going to practice it again. Okay, we're going to solve a triple angle here. Let's go ahead and do number 5. Let's do another sine. Okay, sine 3 theta equals rad 3 over 2. Right? So we're going to first solve this for x. Let me just not make that mistake. Okay. So let 3 theta equal x. Right. So now I really have sine of x equals rad 3 over 2. And I want to find all the fundamental solutions for x. Okay, so number 1, find all the fundamental solutions for x. So I'm going to sine inverse both sides. And the sine inverse and the sine are going to cancel here. And then sine inverse of rad 3 over 2. The calculator is only going to give me one solution, right? What is that one solution? Sine inverse rad 3 divided by 2 should give me 60 degrees, and it does. Okay. Now, the fundamental solutions for x, sine x, is 2 pi periodic, right? The period here is 2 pi over omega, or just 2 pi, right? Or 360 degrees. So I want to find all the places where this function is satisfied. So the first time it's satisfied is at 60 degrees. Okay. So sine of 60 is rad 3 over 2. So this is where the sine value is rad 3 over 2. Right? Where else is the sine value equal to rad 3 over 2? On the other side, where the y value is the same, okay, this is negative x rad 3 over 2. Right? The sine value is still positive, it's just the x changed sign. Now this angle here, the reference angle, is still 60. So my second solution is when rotated from 0, we're looking at 120 degrees, right? So I get x equals 60 and 120, right? So the fundamental solutions for x, let me go ahead and do it here. X equals 60 plus 360k, and x equals 120 plus 360k, right? Now what I want to do is I want to convert those fundamental solutions for x, and I want to convert them to theta. So convert the fundamental solutions for theta. Right? So x is really 3 theta. So I have 3 theta equals 60 plus 360k, right? And 3 theta equals 120 plus 360k. So if I wanted to solve this for theta, I'm just going to divide both sides by 3. And I get theta equals, don't forget to divide both, I'm going to get 20 plus 120k. And I'm going to get 40 plus 120k, right? So these are all the fundamental solutions for theta. and they're a third, right, of the normal solutions, because this function oscillates 3 times as fast, right? It's compressed by a factor of 3. And so we get these solutions. Notice that the period of this function here, right, the period would be 2 pi over 3, which converts to 360 over 3, which converts to 120. So we are adding the fundamental period to our fundamental solutions, but we have to start with the fundamental solutions of a normal trig function in order to get here. All right, so let's do one more thing. Let's find all the solutions from 0 to 360. Okay, most of the time they're going to include one endpoint and not the other. I'm including 0, but they might be like not including 0 and including 360. I'm not sure. But if I wanted to find all the solutions, I'm just going to start with 20 and start adding 120 to it until it gets too big. So 20, if k is 1, I'm going to get 140. Can I add 120 again and still stay below 360? Yes, I can. Right, so I'm going to get 260. If I add 260, sorry, if I add 120 to 260, okay, 380 is too big. All right, So my other solutions are going to be 40, then add 120 to it to get 160, and then add 120 again to get 280. And I think if I add 120 again, it's too large. All right. So here's all the fundamental solutions. Okay. Now, how do we do this in radians? Okay. Let me go ahead and start here and convert it to radians at the 3 theta mark. Right. So 60 degrees is pi over 3 plus 2 pi k. Right. So I'm going to divide everything by 3, right? So this is pi over 3 divided by 3. You guys kind of struggle with this stuff, all right? So if I did pi over 3 divided by 3, I'm going to multiply by the reciprocal, and I'm going to get pi over 9, right? So I'm going to get theta equals pi over 9 plus, if I divide 2 pi by 3, I'm just going to get 2 pi over 3. It doesn't simplify. Okay. So I can do the same thing for the other fundamental solution. 120 is 2 pi over 3, right? Plus 2 pi k. And so if I divide this by 3, then I'm going to get 2 pi over 3 divided by 3 is 2 pi over 9 plus 2 pi over 3 k. All right. It really isn't too complicated except for you guys forgetting how to divide fractions. All right. But there you go. All right, let me do one more example. I know this video is a little on the long side, but let me do one more example, and then I'll save the last 3 for the next video. Actually, no, let me quit now. All right, see you on the next video.